Check it out now, y'all.
NanoHub U, online instruction.
Welcome to tutorial 1.4. And as you know, the purpose of this problem is to obtain these two results, which are summarized in that slide. And these are the quantities. These angular brackets denote an average. And these quantities arose in the context of our discussion this week, where when we were talking about ballistic transport, we needed the average value of the velocity, whereas when we are talking of diffusive transport, we needed the average value of this velocity square, the component of the velocity in the z direction. And as I explained, that when you do this average, depending on whether we are thinking of a one-dimensional, a two-dimensional, or a three-dimensional conductor, we could get one of these three values. And the purpose of this tutorial is to show how you obtain these numbers. And this involves a little bit of calculus, especially the 3D especially. Okay. Now the 1D result actually is fairly straightforward. That is, looking at the average value of Vz, and in a 1D conductor with electrons having a specific energy, which means the magnitude of the velocity is fixed. So the only two possibilities are either plus V or minus V. So those are the only two possibilities for a fixed energy. So it could either be plus V or minus V. So what that means is, if I'm looking at the average value of the magnitude of V, well, if it's here, the magnitude of V is just V. Here it's minus V, but then the magnitude is still just plus V. So since there is only one value, the average value is really just that. And that's reflected in the 1 in that first column. And the same 1 also appears when you average Vz square for the same reason. The only two allowed values are V squared, whether it's plus V or minus V. Okay. So let's move on to 2D, which requires some little more work than that. Okay. Now in 2D, so let me take this off. So now we are trying to do the 2D problem. And let's say we are in this Zx plane. So this is Vz and then this is Vx. And electrons can have any velocity lying on a circle whose magnitude is V. So the magnitude of this circle here, this radius, that's the V. On the other hand, as far as the angle is concerned, it can have any direction. Now I could call this angle theta, and it could be in any direction here. And what we want to do is find the average value of the Vz component. And of course, if it's at an angle theta, then the Vz component is given by magnitude of V times cosine theta. And we'd like to find its average. Now the first question then is that how do you write down the average in 2 dimensions? And what I'd like to argue is that the way you'd find the average is the following. The average of any quantity, the way you'd find it is you'd integrate it over theta, integrate over this entire angle theta, and then divide it by some number, and the question is what number we should use. Okay, first question is over what angle theta should we integrate? And if you get back here, you'll see that theta runs, you see, from 0 to pi here and then 0 to minus pi. So if you wanted to integrate over the entire circle, you would go from minus pi to plus pi. So this end would be minus pi, that end would be plus pi. And you could integrate over the whole thing if you want to integrate over the whole circle. For this problem, it is more convenient just to integrate over half the circle up to here. Just the front part, which is the part where Vz is positive. Because here Vz is positive, here Vz is negative. But what we are averaging, if you look at it, one case it's the magnitude of Vz, which means whether it's the positive side or the negative side gives you the same answer. Or if you square it also, the same story. And so you're better off integrating over just the positive half. Of course, if we averaged over the whole thing, if you were averaging Vz squared, it wouldn't be a problem. If you're trying to do this one, then you have to be careful to include this magnitude of Vz part, which means the parts where it's negative, you have to take the absolute value, which is a little tricky. So you're actually better off just integrating over the front part, which means the positive Vz part, which corresponds to, if I drop this, it's like plus pi over 2 to minus pi over 2. That's this end. So that's the part you want to average. So I'll put a minus pi over 2 here, and I'll put a plus pi over 2 there. Now the next question is, what do I divide it by? And usually the way I think about it is, what you should put here should be adjusted so that if you are finding the average value of 1, let's say I had a quantity that was 1 everywhere, that's 1. Then when I average it, the answer should also be 1. So what I should put here is, I should adjust this value such that if I are averaging 1, I get 1. Now if I are averaging 1, then of course this integral d theta from minus pi over 2 to plus pi over 2, that's easy to do. It's just theta. And if you put in the two limits, you get this minus this, which amounts to just plus pi. So if this were 1, the integral would be pi. And so what I should do here is put a 1 over pi. And that way, the way I'm averaging, if I average 1, I get 1. Okay. Now let's put in what we actually want to average. What do we actually want to average? Well, if I'm trying to find the magnitude of Vz, then what I want to average is V cosine theta. That's the magnitude of Vz. Of course, as I mentioned before, this ordinarily could have become negative and I'd have to take the absolute value. But since in this range it's always positive, I don't need to worry. Done. So now when I integrate cosine theta, the answer is sine theta. And the two limits are minus pi over 2 and plus pi over 2. And the rest of it is V over pi. Now if you put in the limits, sine pi over 2 is 1, sine minus pi over 2 is minus 1. So 1 minus minus 1, that's 2. So this whole thing gives me 2. And so the average value of Vz in 2 dimensions is 2V over pi. And that's then gets us this second result. I guess we obtained the 1D easily. Those were done. What I just did was showed you how you get the 2 over pi. So let's look at quickly then this result, how we get this for Vz squared. Well, once you have set this up, actually this is very easy because Vz squared means you just have to integrate V squared cosine squared theta. Because that's Vz is V cosine theta, so Vz squared is just V square cosine squared theta. Now all that remains is to do that integral, and what you get is something like this. Okay, let me pull the V squared out. V squared over pi, integral minus pi over 2 to plus pi over 2 d theta, And cosine squared theta you can write as 1 plus cosine theta and you can pull out a half. So it is half of 1 plus cosine theta. See? And what you can show then is that when you do this integral, you should get pi, so that pi, you'll get a pi here, and that pi will cancel this, and so you'll have v squared divided by 2. And that is, actually I just said something a little wrong, let me correct it. Cosine squared theta is half of 1 plus cosine 2 theta, not cosine theta. Okay? And so actually when you do the integral, the cosine 2 theta over this limits should give you 0, and the 1 will give you pi. That's what I'd written down here. Okay. Anyway, so now you see the average value is v square divided by 2. And that's exactly what we had here for the second result. That's the half. Okay. So now let's do the 3D one. That's this last column. Now for 3D, of course, the first step is to set up this integral for how one averages anything. That is, you remember, the way we did this is in 2D, we first said, let's write down how you average anything, which is by doing integral d theta and then 1 over pi. And what we need to do is do the same thing now for 3D. Now the way this works is, in 3D, let me just write the result. This is something you should have seen in a class on integrals. Let me just state it and I'll try to explain it a little bit. And the way it goes is, that when you do the integral in 3D, you have integral sine theta d theta, and then an integral over d phi. And we again have to figure out what to put here. So this theta is still the same angle that we had before, but the phi is the angle that runs out of the blackboard and then back into the blackboard, goes around this way in the xy plane. That's what the phi direction is. Now, usually the way these integrals are done, if I wanted to integrate over the entire surface of the sphere, then what I'd have to do is, I'd have to integrate theta from 0 to pi all the way up to here. So normally what people would do is integrate from 0 to pi, and the d phi integrates from 0 to 2 pi. Now, in 2D, if you remember, when we were integrating over theta, I said if you want to integrate over the entire circle, you should go minus pi to pi. And then we said, well, we'll only do half. So we'll go minus pi over 2 to plus pi over 2. In 3D, you only go 0 to pi, only this side, because the phi kind of takes care of this one, because the phi angle goes round like this and comes back. And this is the part, as I said, is one of those things, if you have taken a course in integral calculus, they go over it in great detail. And I'm assuming you have seen this before, and I just want to remind you where this integral comes from. This is what would be involved if we are trying to find, say, the surface of a sphere. As you know, a sphere of radius r, the surface is 4 pi r square. So if r is 1, it should give you 4 pi. And the way you would obtain it is by doing this integral. You see, what would happen then is, this integral would give you 2, and that integral would give you 2 pi. And together it would give you 4 pi. That's this surface of a sphere. See? Now, for our purpose, since we want to integrate only over the positive side of this, here instead of going from 0 to pi, I'll go from 0 to pi over 2. What that means is, when I do this integral, ordinarily, what I'd get is 1 and not 2. So that would give me sort of just half the surface of the sphere, only this half, not this half. Okay. Because again, I'm only integrating over that part where Vz is positive. Okay. Now, what should I put here? Well, again, the same principle. If I were averaging 1, I should get 1. If I'm averaging a quantity, that's always 1. Well, if this was always 1, this integral would be 2 pi, so let's put a 2 pi here. So this is how you average anything in 3D. So now let's get down to what we actually want to average, which is V cosine theta. That would be the first one. So really trying to average V cosine theta. And now if you do this integral, so you see nothing depends on phi, so this part will still give you 2 pi. But then this cosine theta we have to pull over to this side. So what you'd get is, so this 2 pi cancels that. And so that takes care of this much. And then we are left with the rest of it, which is V integral 0 to pi over 2 d theta sine theta cosine theta. Write that properly. Now sine theta cosine theta is actually half of sine 2 theta. So what I could do is put a half there and make this sine 2 theta. Okay. And this then would get you this first result here, the half. So that's that one. Now how do you do the 1/3 one? Well, again, the basic integral structure is still the same. Okay. It's just that instead of V cosine theta, we now write V squared cosine squared theta. So again, same story. Integral d phi, this part of it gives me 2 pi, which cancels that one. So I just need to do this integral, which is V square integral d theta sine theta and then cosine squared theta. Integrated from 0 to pi over 2. Now the way you do this integral is, you could give cosine theta a name. Let's call it x. Nothing to do with the direction x, just some x. So if cosine theta is x, then d theta sine theta is dx. And so when I integrate x squared dx, what I get is x cubed over 3. And of course the limits on x, x is cosine theta, so you'll notice this is like 1. At that limit, it's like 1. And at that limit, it's like 0. By the way, I missed one small point, and that is if cosine theta is x, then d theta sine theta is actually minus dx. And that minus would actually reverse the two limits of the integral. Anyway, the bottom line is, the limits are 1 and 0. So x cubed over 3, when you go from 0 to 1, the answer you get is 1/3. And that then gets us this last one. So just to sum this up again, in all of this, what we were trying to do is find the average value over all the positive values of Vz. All the positive side. 1D, it's trivial. In 2D, the way you do it is, you have to do this integral over d theta. We went through that. When it's 3D, it gets a little harder because you have to integrate theta and also phi. And that's what we set up here on how to do the average in 3D. Thank you.